Good day and welcome to Big Bad Tech. I'm your instructor, Jim Pytel, and today we'll examine several illustrated examples of the combined gas laws. This lecture operates under the presumption the viewer has watched the combined gas law lecture, available at the Big Bad Tech channel. If you haven't watched this lecture yet, or only dimly recall its contents, please take the time to do so now and return to this lecture when you are so qualified. Before we begin, I wanted to mention that the circuit simulations and schematics in this lecture were created using Automation Studio, a product of FAMIC Technologies. This is a tool I'll be using with greater frequency in upcoming lectures. If you need more information about Automation Studio, visit their website at www.famictech.com. Mastery of the combined gas laws necessitate active participation on your part, and as such, I'm encouraging you to please pause the lecture when asked to do so and attempt the example problems on your own. If your answers do not match those illustrated, by all means, feel free to rewind the lecture and correct any mistakes you may have made. Before we head into the illustrated examples, a quick review of the combined gas laws. You'll no doubt recall certain conditions define the standard cubic foot of air, notably a temperature of 68 degrees Fahrenheit, a relative humidity of 36%, and atmospheric conditions at sea level, i.e. 0 psi gauge or 14.7 psi absolute. Only in these conditions will a standard cubic foot of air occupy 1 cubic foot of volume, being a cube 12 inches high, 12 inches wide, and 12 inches deep, or 1,728 cubic inches. As you are no doubt aware, at higher pressure conditions, a standard cubic foot of air will occupy less volume, whereas at lower pressure conditions, the same cubic feet of air will occupy more volume. But importantly, it remains a standard cubic foot of air. In this capacity, a standard cubic foot of air is not a measurement of volume, but rather a unit of quantity, i.e. a fixed mass of gas that can be compressed or expanded. The conditions defining the standard cubic foot are simply a snapshot of some agreed upon state for a basis of comparison. Let's try 3 quick thought experiments involving the combined gas laws. Thought experiment 1. At sea level, 3 identical balloons are filled with 1 standard cubic foot of air and then placed in 3 different locations. One on top of a 68 degree Fahrenheit mountain 10,000 feet in the air, one on a 68 degree Fahrenheit beach, and another at the bottom of a 10,000 foot deep oceanic trench, also at 68 degrees Fahrenheit. My question to you is this: how will pressure, less on the mountain, more at the bottom of the ocean, affect the volume of these balloons? Note, temperature is being kept constant in all 3 scenarios. Undoubtedly, the balloon at the top of the mountain will be larger than the balloon on the beach and much, much larger than the one at the bottom of the ocean. Importantly, each balloon still contains 1 standard cubic foot of air. I must remind you, a standard cubic foot of air simply occupies more or less volume at different pressure conditions. A standard cubic foot of air is not a measurement of volume, but rather a quantity of gas. This thought experiment perfectly illustrates Boyle's law, which states given constant temperature, pressure 1 times volume 1 equals pressure 2 times volume 2, where the subscripts 1 and 2 mean initial and final conditions. Given 3 known properties, one can solve for the 4th unknown property. Thought experiment 2. At sea level, 3 identical balloons are again filled with 1 standard cubic foot of air and placed in 3 different locations, all at sea level. One hovering over an active volcano, one on a 68 degree Fahrenheit beach, and another in an open-sided Minnesota hockey rink midwinter. My question to you is this: how will temperature, more in the volcano, less in the hockey rink, affect the volume of the balloons? Note, pressure is being kept constant in all 3 scenarios. Undoubtedly, the balloon in the volcano will be larger than the one on the beach and much, much larger than the one in the hockey rink. Importantly, each balloon still contains 1 standard cubic foot of air. Again, the standard cubic foot of air simply occupies more or less volume at different temperature conditions. This thought experiment perfectly illustrates Charles' law, which states, given constant pressure, volume 1 divided by temperature 1 equals volume 2 divided by temperature 2, where again the subscripts 1 and 2 mean the initial and final states. Given 3 known properties, one can solve for the 4th unknown property. Lastly, thought experiment 3. 3 rigid aluminum containers are filled with 1 standard cubic foot of air and placed in 3 different locations. One stuffed on a roaring campfire, one on a 68 degree Fahrenheit beach, and another encased in a glacier. My question to you is this: how will temperature, more in the campfire, less in the glacier, affect the pressure exerted by the confined gas inside the rigid containers? Note, volume in the rigid containers being kept constant in all 3 scenarios. Undoubtedly, the container in the campfire will experience more pressure than the one on the beach and much, much more pressure than the one in the glacier. This thought experiment perfectly illustrates gay-Lussac's law, which states given constant volume, pressure 1 divided by temperature 1 equals pressure 2 divided by temperature 2, where again the subscripts 1 and 2 mean the initial and final conditions. Given 3 known properties, one can solve for a 4th unknown property. Lastly, it needs to be said that Boyle's law, Charles' law, and gay-Lussac's laws only work in terms of absolute, not relative temperatures and pressures. Temperature must be measured from absolute zero, something the Fahrenheit and Celsius scales do not do, but the Rankine and Kelvin scales do. Similarly, pressure must be measured from perfect vacuum, something the gauge scale does not do, but the absolute scale does. This implies that one must be adept at converting temperature from a relative scale like Fahrenheit or Celsius to an absolute scale like Rankine or Kelvin, and vice versa, as well as skilled at converting pressure from gauge to absolute and vice versa. Unless explicitly specified otherwise, all pressure measurements are gauge readings. You'll recall 0 degrees Rankine is roughly equivalent to negative 459.7 degrees Fahrenheit. 0 degrees Kelvin is roughly equivalent to negative 273.2 degrees Celsius, and 0 psi gauge is roughly equivalent to 14.7 psi absolute. To yield usable results, one may necessitate additional conversions depending upon the desired units. This concludes the brief review. Let's begin with the illustrated examples. Problem 1. Consider a rigid metal receiver pressurized to 95 psi in a 68-degree Fahrenheit workshop, then brought out to a job site at Furnace Creek Ranch in Death Valley, California, and left in the hot sun, reaching a temperature of 134.1 degrees Fahrenheit. Let's say the safety relief valve opens at exactly 120 psi. Does the safety relief valve blow? To see if it does or not, determine the pressure in the receiver in the elevated temperature condition. We're presuming the volume of the rigid metal receiver remains constant. By all means, pause the lecture and try this on your own. If you're tracking, you should have obtained the following results. This scenario is clearly calling for application of gay-Lussac's law. Given constant volume, pressure and temperature are related in the following fashion. P1 over T1 equals P2 over T2. Given increased temperature at the job site, pressure in the receiver will undoubtedly rise. Is it enough to blow the safety relief valve? We'll see. First, convert the two temperatures to the Rankine scale, and then convert gauge pressure to absolute. 95 psi gauge is roughly equivalent to 109.7 psi absolute. 68 degrees Fahrenheit is equivalent to 527.7 degrees Rankine, and finally 134.1 degrees Fahrenheit is equivalent to 593.8 degrees Rankine. We know P1, T1, and T2. We want to determine unknown pressure P2. An algebraic manipulation of gay-Lussac's law solved for P2 demonstrates P2 is equal to P1 times T2 over T1. Substituting in the given values, P2 is found to be roughly 123.4 psi absolute. You might say, yes, the safety pressure relief does indeed blow, but you're forgetting an important final step. This is pressure inside the receiver expressed using the absolute scale. You need to convert this back to the gauge scale. A unit conversion demonstrates 123.4 psi absolute is roughly equivalent to 108.7 psi gauge. The safety pressure relief valve stays closed. Problem 2. This is a pretty fun one. Consider this simple pneumatic circuit consisting of two identical unloaded cylinders. The regulator is set to 60 psi. When I open valve 1, unloaded cylinder 1 extends, and pressure in gauge 1 rises and stabilizes at 60 psi, as one might expect. If I close valve 1, cylinder 1 remains extended, and pressure gauge 1 remains at 60 psi. All right, here's two questions. What happens to unloaded cylinder 2, and what does pressure gauge 2 read if I open valve 2? If you're looking for cylinder dimensions, pick some. The key is cylinder 1 and cylinder 2 are identical and unloaded. For the purposes of this problem, we're assuming temperature remains constant. Again, cylinder 1 and cylinder 2 are identical and unloaded. I'll give you a hint. I'm basically doubling volume when I open valve 2. By all means, pause the lecture and try this on your own. If you're tracking, you should have obtained the following results. This is clearly a Boyle's law problem, which relates pressure and volume at constant temperature. When valve 2 opens, the pressurized air trapped in cylinder 1's cap end expands into cylinder 2's cap end. Given both cylinders are unloaded, cylinder 2 extends. Given both cylinders are identical, we've effectively doubled volume, such that V2 equals 2 times V1. What does pressure do? Given volume doubled, you might rush to the incorrect conclusion that pressure is in half and expect gauge 2 to read 30 psi. But not only is that wrong, it is absolutely wrong. Note the emphasis on the term absolute. It is categorically incorrect to say that if volume doubles, pressure is cut in half. It is, however, entirely proper to say if volume doubles, absolute pressure is halved. 60 psi gauge is equivalent to 74.7 psi absolute. Given V2 is equal to 2 times V1, and solving for pressure 2, it's half of P1. This yields an absolute pressure of 37.4 psi absolute, which is equivalent to 22.7 psi gauge. Let this be a lesson about those tricky problems in textbooks and tests which feature statements like pressure doubles or temperature doubles. Using the absolute scale as one must when employing the combined gas laws, 50 psi gauge is not half as much pressure as 100 psi gauge, nor is 80 degrees Fahrenheit twice as hot as 40 degrees Fahrenheit. If a problem doesn't specify absolute or gauge, seek clarification from your instructor.